All right. 9.3 is called saving money. Okay, so that's pretty generic. That doesn't really tell us much. But what we're going to be doing in this section is looking at, first of all, a very nice natural extension of the this formula. Not even an extension of it, just like reorganizing it. We're going to look at how to find the so-called present value. In other words, how much money you have presently needed in order to reach a certain amount, a certain future value that you might have as a goal. So that's the first thing we'll look at, and it'll be very natural, just reorganization of this formula. And then we're going to start looking at calculations with annuity. So an annuity is just going to be, we're going to be addressing the question that we haven't asked yet, which is, what happens if you are making regular payments into the savings account? Which is a very natural question, right? If you're making monthly payments, then what will the amount be after a certain number of, certain amount of time, and etc. So let's dive into the first thing, which is calculating present value, which we'll call PV, is the amount, so money, of principal needed now, so present meaning now, in order to reach a future value amount. So you'll notice a lot of these formulas I'm going to start replacing. I'm going to replace P with PV, and I'll end up replacing A with FV for future value. Okay. This PV, present value, is calculated with the formula PV is equal to, now it's just this P. It's just the principal. It's just a special kind of principal specifically for making this calculation the amount of principal needed in order to reach a future value amount. Now, if I wanted to solve for this capital P here, how do I isolate P? Like algebraically, how do I isolate this capital P up here? And you may say, oh my goodness, I have no idea. Look at all this crap attached to it, right? Like, how do I deal with that? Well, P is just attached to this crazy looking thing by multiplication. In other words, just divide this whole thing over. That's all you have to do. So it looks like a new crazy formula, but it's really just this formula reorganized with one little step, which is to divide that entire thing over. So if you have some future value amount in mind, and you have some rate from your bank account and some compounding amount, from your bank account, and also how long you're going to be investing, then this formula tells you what principal is needed to reach your goal, which would be A. A is your goal, like the amount that you want in the account. Okay. So let's run example 1 now. Just practice using this formula. State College predicts that in 18 years it will take $150,000 to attend the college for 4 years. So let's say tuition in 18 years will be $150,000 for 4 years. For a traditional 4-year college experience. Let's say you have some chunk of cash that you want to save for a newborn that you just have. You want to go ahead and start saving right now so that in 18 years you'll have some college fund money for this child. How much money should you put into an account? Okay, account with an APR of 4% compounded monthly in order to have how much? How much do you need? Well, 150,000. In the account after how long? Well, you've got 18 years roughly, right? Until that child is ready to go to college. So this problem is actually a little bit longer in the textbook. They give you a little bit more details, but I'm just kind of paraphrasing it, right? So just saying tuition at some college, just some generic college, will be $150,000 for a 4-year college, experience, 4-year degree. You've got 18 years to save because you're saving right when the baby is born, and you've already got a savings account in mind. And it has an APR of 4% and it's compounded monthly. Okay, so let's run this calculation then. We want to know what is the present value you need to go ahead and drop into this account right now in order to have this much in the account after 18 years. So we're going to say our goal is 150,000. That's the amount in the account that we desire, right? Over 1 plus our rate, which is 0.04, always remembering to write that percent as a decimal, over n, which n is the number of compounding, so monthly means n is happening 12 times per year, so n is 12. And then up in the exponent position, we have 12, n, which is 12, times 18 up in the exponent position because t is 18. Now when you're running this in the calculator, you're going to want to be careful. Let me scoot all this up here. Well, we want that formula, so let's do that. You're going to want to be careful because you don't want to mess up the order of operations. So there's a few different ways we could do this. You can go the parentheses heavy route where you just kind of go straight for it. 150,000 divided by, now I'm going to need to wrap this entire thing in parentheses, so let me see, I'm going to say double parentheses, 1 plus 0.04 divided by 12, close the first set of parentheses, raised to, now my exponent needs to be wrapped in parentheses. That little product up there needs to be wrapped in parentheses, 12 times 18. And now I'll close that final set. And that's going to give me the answer. No, I messed something up. Hang on. $731,000 is not. Oh, wait, no. I'm misreading this. Okay, that is right. So we're getting approximately $73,100. They tell us what to round to. Yeah, we'll just leave it as a dollar amount. And so there's 31 cents there, but when the numbers are this big, are you really worried about a few extra cents? Probably not. Okay, so this is how you can run it in the calculator all at once. You got to make sure that you're wrapping your exponent up here in parentheses, and also I had to wrap my entire denominator in parentheses to make sure that the calculator knows I'm dividing this whole thing. Okay. Now, if you don't feel comfortable doing that, you can do it this way. You can just figure out what this denominator is. 1 plus, parentheses, still need parentheses for it. 1 plus 0.04 divided by 12, and then raised to, so this should seem very familiar to the previous calculations we've done. So this is what the denominator is. Now, you may have before thought, okay, I'll just write this down and save a bunch of the digits and then erase it and then type 150,000 divided by and then just write that number back in. But there's a more efficient way to be able to save all of the digits. What you want to do is you want to invert this number, because right now you've got it as like a numerator, but you want to invert it, put it in the denominator. That's what this little button is for, x to the minus 1. On your calculator, it might be 1 over x or 1 over y or something like that. You're going to smash that button, and that flips it. That takes it and flips it. Now it's in the denominator, and now you can just multiply it by 150,000. And there I get the same answer. So you need to know how to run this in your calculator. Okay. You need to make sure you can figure it out. Just figure out something that works for you so that you can replicate this and get this with these numbers and get the same answer. Okay. Okay. So this should seem very natural, though. It's a very natural extension of this compound interest formula, literally just dividing this whole thing over to find a present value needed for some goal amount. So looking at this, I would say that baby that was just born better get a scholarship or something, because if this is how much money you would need when the baby was born to drop into the account to be able to save $150,000. That's crazy. Who has that much to just... If I had that much, I would not want to spend it on a baby. Well, I guess it's a good investment in their future, but anyways. Okay. Let's talk about annuity now. Okay. So let me officially define annuity. An annuity is a sequence of regular payments made into an account, which is a very natural thing, right? So if you have it set up with your bank that $50 from every single one of your paychecks goes into your savings account, that would be an annuity. It's a sequence of regular payments. The annuity is not the payment itself. The annuity is the sequence of payments. That's just a subtlety, though. Now, it can also be something that's taken out. Over time. So just over time. So an annuity, probably we're going to be dealing mostly with payments being made into an account, because we like to think of, our examples are always savings accounts. So you would be making payments into the account. But an annuity can also be a sequence of things sequence of payments regularly being taken out of the account. So if you've got a compound savings account and an annuity set up, then not only will it be gaining interest every time it compounds interest, but it'll also, you'll be putting money into the account too, so it'll be gaining more interest on the next payment. So this is the best thing to do, is obviously to have a large lump sum of money to put in there so that it starts gaining interest immediately, but then to also make regular payments to increase the amount in the account even more. I don't think I need to explain how that would be a good idea. Here is the formula for the future value. So now I'm going to start replacing A with FV for future value, because that's what our book does. And I don't want to introduce my own notation and end up confusing you, so I'll stick with FV. Okay, so FV, the future value in the account, is going to be equal to the payment times, now this formula is going to look kind of like a lot, but remember, as long as our calculator work is strong, then it won't be too bad. Okay, so this is looking familiar. Oops. This, right, 1 plus r over n raised to the nt, that's part of the compound interest formula. And then all over r divided by n. Okay, now let me define each of these things, even though we already know what r is, right? R is the APR, but where PMT is the regular payment made, okay, probably guessed that, it's the regular payment. R, I'll go ahead and write, is the APR, we already knew that. N is the number of times this payment per year. So if it's monthly, if you're making monthly payments, then N would be 12. And of course, T is years. T is just time in years. Okay, so let's run an example using this formula. Okay, so let's say you begin placing $75 per month into an annuity savings plan beginning in August 2014. The savings plan earns 2.5% APR compounded monthly. First, part A, determine the amount you personally put in the savings plan over 10 years. Part B, calculate the future value of the savings in August 2024. There we go. Okay. Part A does not need a formula. Part A is just asking, how much are you putting into the savings plan over 10 years? Well, you're putting in $75 per month. So I could say, let me say it this way, $75 per month. Use a little bit of dimensional analysis here and say, okay, well, that's how much per year. Well, if I want this to be measured in years, then I want per year, so 1 year is equal to 12 months. Right, I want months to cancel out, so I'll just be left with years. And that will give me 75 times 12 will give me $900 per year. That's per 1 year. I don't need the 1 now. I could just write per year. And then what I'll do is I want this to be for 10 years. So I'll multiply by 10, right, to get $9,000 for 10 years. Oops, 10 years. Okay. So $9,000 is the answer for part A, $9,000. No formula needed there. That's just understanding how many months are in a year and how many years you're going to be doing this, right? Okay. Part B is a little bit more involved, right? We know that that does require a formula, specifically the future value formula, which says future value is equal to the size of the payment times one plus r over n raised to the nt minus 1 all over r over n. Lots of things to plug in here. So 75 is the size of the payment. This is happening monthly, by the way. So we'll say 1 plus 0. What was the interest rate? 2.5%, so that'll be 0 to 5. And then over 12, because this is happening monthly, raised to 12 times 10, because we're still talking about 10 years, right? The future value in August 2024, and it started in August 2014. And then minus 1, I forget that minus 1, all over the rate, 0.025, that's a 5, over n, which is 12. Okay. This is going to be approximately, and let's see what we get here. Can I do this all at once? Yes. I'm going to do 75, let me get, there we go, 75 times, and then parentheses, yep, another set of parentheses, so now I'm here, 1 plus 0.025 divided by 12, close the first set of parentheses, raise my exponent. I'm just going to go ahead and say, 12 times 10 is 120, so I'll just do that in my head so I don't need to wrap my exponent in parentheses because it's not written as a product. Then minus 1. Now I'll close that second set of parentheses, so that's the bracket here. And then I can go ahead and hit equals. That's fine. That's what this whole numerator would be with the 75 included. And now I'm going to divide. Now when I divide here, I need to open parentheses and wrap this thing in parentheses, so 0.025 divided by 12, close that parentheses, equals, there it is. Sorry, let me put it there. All right, 10212, and I'll just round to, let's see, 89 cents, round it, so 90 cents. There we go, $10,212.90 after 10 years. This is starting at 0. Okay, this is starting at 0. This is not putting in a big lump sum, like a big principal, and then also having that compound interest and also putting in monthly payments. This is starting at ground 0, okay? And this is over the course of 10 years. And you may say, like, oh my goodness, that's a lot, that's great, but how much did he put into the account? Or, well, sorry, you, I guess. In the example in the textbook, it's a guy putting this money into the account, but I framed it as you begin placing this much into the account. So how much did you put into the account? Your own money from your check every month. $75 every month for 10 years. That's $9,000. So how much interest did you actually earn? how much interest. So in other words, like how much did the bank give you just for having your money in there? Well, you would have to take this 10,212.90 minus the money that you actually put in there, which would be this much, right? Just doing 10,212 minus 9,000. Okay. I said that I would derive, did I say anything about this for this formula? This formula for future value here, let's not. There's some parts of it that we could make sense of, but let's not take the time to derive it. It'd be really interesting, but I think that the algebra is kind of beyond the scope of this class, so we will just kind of look at the formula and say, oh, it kind of makes sense because I see some pieces here that I've recognized from previous formulas. So, you know, okay, it seems familiar, and that's pretty much all we're going to say with it. Okay. So, what would the next step be? Let's do example 3, using the same formula, but just a slight twist to the problem. Calculate the future value after 6 months of monthly $50 payments. With an APR of 12%. So I want to make something clear here that maybe I didn't make explicitly clear enough when I introduced this annuity thing. This is different from compound interest, right? So a compound interest account, in terms of savings accounts, a compound interest account, the idea is you have this big chunk of money and you just plop it in there and let it sit there and gain interest. The annuity savings account, or so-called savings plan, is not that. It's different. It's like you're starting at zero and making monthly payments. It's a different kind of calculation. Okay, and also notice in this problem, well, actually, before I even talk about this problem, in example 2, we were given that our account compounded monthly, right? But that's not why we plugged in 12 into our annuity future value formula. This 12 was because we were making monthly payments. Monthly payments, okay? The compounding for the savings account is not important when we're calculating our future value for our annuity. It's a different kind of savings account. And, you know, it just depends on your situation, you know. Okay, so calculate the future value after 6 months. So we've got future value is equal to payment times 1 plus r over n raised to the nt minus 1, close that parentheses, all over r over n. Okay, one thing to note here, in fact, let me just write all these off on the side. Let's just write them all. Payment is $50, okay. Our APR is 12%, so 0.12, written as a decimal, just dividing by 100 to get it as a decimal. N is monthly, so 12. And t, what is t? What is the time span? 6? No. T is measured in years. How many years have passed if 6 months have passed? Half of a year, right? So, okay. That's the twist to this problem. Time is 1/2 because only 6 months had passed. And time should be measured in years for this formula. It's important that time is measured in years because of the relationship between n and t. N is how many payments are being made per year. So we would, if you wanted time to be measured in months, you would have to adjust n as well, and you don't want to deal with that. So easier to just think 6 months means half a year. Okay, so here we go. We'll say 75. No, sorry, that was the last payment. Sorry. Let me just restart that here. 50 times 1 plus 0.12 over 12. You notice 12 keeps popping up. Yeah, monthly payments does seem very natural, right? So up in the exponent here, I'm going to say 12 times 0. So that's times 0.5 up in the exponent, and then minus 1. And then all over 0.12 over 12. So you notice 12 keeps popping up as the n value for these because monthly payments, it just really does seem natural, right? Maybe though you get paid bi-weekly or twice a month, every 2 weeks, and you are putting away money from both of those checks every month, then your end would be 24, right? Because that would be 24 payments per year if you were doing it every 2 weeks. Okay, so I'm ready to plug this in. Scoot this over and put the calculator here so you can see what I'm doing. 50 times 1 plus 0.12 divided by 12, close that, raised to the, so I'm going to wrap this whole exponent in parentheses, 12 times 0.5, close that, and then I'm going to say minus 1, close that, so that's my whole numerator, and I hit equals, divided by 0.12 divided by 12, that's the denominator there wrapped in parentheses, and I'm getting approximately, so I'm going to round, $307.60. So this is after half a year, you're putting in $50 per year, $50 per month for 6 months. This is how much you would have in there. By the way, how much are you putting in there if you're putting in $50 per month for 6 months? Well, 50 times 6 is 300. So how much interest have you earned? Well, $7.60. Okay. Okay, so what is next? Example 4 is pretty much another routine calculation here. So I'm going to skip that and look at this interesting few paragraphs between page 490 and 491. So we have 2 different investment strategies here. Kurt and Johnny both graduate from college on the same day. Kurt decides to start saving for the future right away and begins depositing $200 per month into an account with an APR of 7.5%, and after 15 years, he stops investing and never makes another deposit. So this is what Kurt does. He invests his payment is $200 per month. $200 per month. APR, I'm just going to kind of paraphrase all this. APR of 7.5%, and it's 15 years. And then he stops and he never makes another payment again. He just lets the money sit there. Let's calculate his future value. Oops, 200 times 1 plus 0.075, that's R, over 12 monthly, right, per month, so n is 12, raised to the n times t, so 12 times 15, and then minus 1. And in the bottom, I'll have my rate, 0.075 over n, which is 12, again, per month. Let's calculate that. Then we're going to compare to another strategy. No, that's not right. I forgot to close my parentheses. Redo it all. Okay. 1 plus 0.075 divided by 12, close that, raised to 12 times 15, close that, minus 1, then close that, equals. Then, oh, maybe, sometimes the calculator does know what you're trying to do, even if you don't close your parentheses. Okay, so he's getting approximately $66,222. Let's just leave it like that. $66,222. Now, Johnny, the same day that Kurt stops investing money, so 15 years later, Johnny decides to start investing. $200 per month. Same as, let's say, the same bank, same savings per month, APR of 7.5%. But the question is, because Kurt's account is going to keep gaining interest, even though he's never going to make another payment again. Because it does have an annual percentage rate, it's going to keep gaining interest, right, based off of that APR, without that payment of $200, though. And they tell us later in the paragraph that his savings account actually compounds monthly. So this is going to keep compounding interest monthly, this Kurt's money. Now, the question down here is, how long? So 15 years have passed, Kurt stops investing, his $200 per month, just lets the money sit there and gain interest on its own. So he's turned it into like strictly a compound interest account. And now Johnny, at the same day, decides to start investing. And the question is, how long will it take for Johnny to catch up to Kurt? Okay. Well. So I'm going to quickly do some calculations. First of all, I know that after 15 more years, Johnny's future value will be approximately what Kurt's was, right? So this is at the, like, altogether the 30-year mark, right? So this is, for the first 15 years, Johnny didn't invest at all. So at 15-year mark, this is where Kurt is and Johnny's at 0. 15 years later, Johnny is at this much. So how about this? Let's keep this straight here. So we'll go like this. So we'll say the end of 15 years, and then we'll just like track it. Okay, we'll track it for a little bit. Okay, let's do 30 years, and then we'll pick some other based off of what kind of numbers we get here. So at the end of 15 years, Johnny has $0 because he only started investing on the first day after 15 years, and then at the end of 30 years, he's got the same amount that Kurt had at the end of his 15 years. So let me write all this down. So at the end of 15 years, Kurt has this much, and now his account keeps gaining interest, compounded monthly. With that principal of 66,222, which is still in my calculator here. So that turns into his principal. So now I'm going to use that old formula, principal times 1 plus r over n, his rate is 0.075, divided by n, which is 12, because his savings account compounds monthly, So the n is the same in both formulas here because the savings account compounds monthly and they're making monthly payments. So it just coincidence, it ends up being the same. And I want to calculate this for 15 more years, right? With this principal, this is his like starting amount from 15 to 30. And let's see what that gives me. Oh, wait a second. Let me redo that. That seems crazy. So that principal times, so that principal, 1 plus r, which is 0.075, divided by n, which is 12, raised to the n times t. T is 15 again. Oops, 15. From 15 to 30. Okay. I guess that is right. 2 million. Oh no, I'm misreading it again. I don't know why. I haven't been misreading my calculator like all day today. I thought it said 2 million at first, and that was like, that seemed crazy. It's still a lot though, $203,265, and I'm not going to worry about the cents here. Okay, so this is where Kurt is after 30 years and where Johnny is after 30 years. So it's a huge gap here. Let's say 60 years. Let's go to all the way to 60 years and just see where they would be at. So they are both old now, because this is 60 years after they graduate college, right? So they are getting old. Let's see how much is in this in Johnny's account. So his principal, 66,222 times 1 plus 0.075 divided by 12 because it compounds monthly, raised to the 12 again because it compounds monthly, times time. Now time here is the gap is 30 years, 30 to 60, so I'll say raised to that. And he should have a healthy amount in his account. It looks like 623,912, 623,912. Let's see what Kurt has. So again, based off of, well, I can go based off of this number. This is his new principal. That's fine. $203,265 times 1 plus 0.075 divided by 12 raised to the 12 times, again, the gap here is 30 years. And now Kurt has now become a millionaire, right? 1,900,000, nearly $2 million. So I'm going to go ahead and give it away and say that what ends up happening is Johnny can never catch up to Kurt. Kurt just invested too early. Kurt just invested too early. I just realized I made a mistake. I calculated Johnny's... this still holds. This is the point of the exercise, that Johnny can never catch up to Kurt. This number's not quite right, though, because Johnny, the point that makes it even crazier is that Johnny never stops making the $200 per month payment. He keeps making that. I calculated it as if he didn't keep making it. I calculated it via just the normal compound interest formula formula. So I should have used the future value annuity plan formula. So let me redo that. Hang on. So I need to think about going all the way from 15 to 60 years. 15 to 60 years. So, okay, here we go. Payment is $200 per month times, double parentheses, 1 plus 0.0575 divided by 12 because it's a monthly payment, raised to the 12 times from 15 to 60 years. That's 45 years. Okay, and then minus 1, close that parentheses, they're divided by 0.075 divided by 12. There we go. He has more. I didn't. I calculated as if he stopped making payments as well. But the point is that makes this problem so crazy is that Johnny keeps making payments. So he's going to have even more money than we originally thought. But also he still can never catch Kurt. Even if he keeps making $200 payments for the rest of time, Kurt just had too much of a head start, and that compound interest, when your money is this big in your account, compound interest starts to really, really take off. They draw a nice little graph of this, actually. Right here, you see Kurt is the... Oh, they use blue for Kurt and red for Johnny. I did the exact opposite over here. Oh, well. So you can see, though, Kurt's money is exploding up much faster than Johnny's, and Johnny's going to keep growing, but he'll never be able to catch up to Kurt's money because Kurt just invested too much sooner, or too much earlier. All right, so now let's move to the next formula, which is going to be the annuity formula for finding payment amounts. It's a very natural extension of the annuity formula for future value, which we've been using for the past few problems. So the other formula was, let's write it down first. This future value is equal to payment times all of this craziness. But now, what if I want to know the payment needed for a future value goal? Right? I've got a goal of whatever amount, and I want to know what is the future payment I need to make if I've got an annuity type account. Now, the very first example we worked sounds similar, but remember that first example we worked in this section was based off of a compound interest savings account. Now we're talking about an annuity savings plan. Okay. So what I need to do is I need to solve for payment here, but that just means dividing by this giant thing, and it's gonna basically that just flips it upside down. So it's gonna look just like this. It's gonna be payment is equal to FV, future value, times, and then that giant fraction, except it's just flipped upside down. That's all that happens when you divide by a fraction. Just flips it upside down. There it is. There's the formula. So this tells you the payment that you would need to make for some future value goal with some given APR, and depending on how often you want to make the payment and for how long too. You have to know, you have to have all that in mind in order to be able to solve for the payment here. So all of these things are the same thing that they were. R, N, T, they're all the same that they were in the last formula. So I won't rewrite all that. So this is example 5 in the text. I skipped example 4 and instead talked in detail about the Johnny versus Kurt thing. So you can go back and work example 4 if you'd like. It's very similar to the previous example 3. So, okay. So example 5, though, says, suppose you'd like to save enough money to pay cash for your next computer. Okay, so let's say the goal is to save $3,000 over the next 3 years. Hang on. They phrased this problem very badly. Oops, I missed the L. They said, what amount of monthly payments must you make into an account that earns 1.25% interest in order to reach your goal? I'm going to say it this way instead. What monthly payment? Do you see why I think that's badly worded? I'll explain after I'm done writing. Uh, 1.25% interest. So the way they phrase this problem, let me show you what they wrote. They say, what amount of monthly payments must you make into an account? Oh, you can't even see this. There we go. What amount of monthly payments, all the way down here, must you make into an account that blah, 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 blah. To me, that's asking the question, how many payments, right? Doesn't it sound like that's what they're asking? But that's not what they want. What they want is, what is the size of the monthly payment, right? Which is exactly what this formula tells you. All right, so I'm not going to rewrite the formula since it's right there. I will plug things in though. So PMT is equal to future value, that goal. Whoa, that's supposed to be a 3. So 3,000 times, big fraction bar, R over N. So R is 0.0125. Again, just dividing that percent by 100 to get my percent as a decimal. 0.0125 there. Over N. N is 12 because they say right there, monthly. Okay, now in the denominator, I'm going to have 1 plus 0.0125. That's 0.125 over 12 raised to the 12 times t. T is 3 years. T is 3. Then minus 1. Then I'll close it. Okay. Gonna have to be careful here. What's the most efficient way of doing this? Probably get this denominator, then invert it, and then multiply by this stuff that's on top. So I'm gonna say one plus 0.0125 divided by 12 raised to the 12 times 3, hit equals, don't forget the minus 1, so minus 1. Okay, now that's my denominator, but I need to invert it, right, because as I've calculated it, the calculator doesn't know it's supposed to be in a denominator right now, so I invert it, then hit equals. Okay, now I'm going to multiply by this and this, so I'll say times 3,000. I can go ahead and hit equals there if I want. And then times parentheses 0.0125 divided by 12. And I'm getting approximately $81.82. So that's the monthly payment that you would need to make in order to save $3,000 over the next 3 years, about $81.82. Now, if there was no interest involved here, how would you solve this? If it was much simpler, no interest, and you were just stuffing money under your mattress, you would just take 3,000 for three years, right? So divided by, if you're making monthly payments, every month you're stuffing some cash under your bed. That's 36 months, right? For 3 years, 36 months. That's how much money you would need to stuff under your mattress each month. $83.33. So having this thing earn a little bit of interest is a little bit better, right? It's a little bit better. But again, you don't really see that interest really taking effect until you're talking about big sums of money, right? This is, relative to the numbers we've seen in this chapter, this is not very big, right? So, and neither is this interest rate. Well, that kind of depends. But, So interest is not really playing a huge role to help you here. If you're only talking about saving for only 3 years, for only this much amount, and you're only going to be making like less than $100 per month in payment, then we wouldn't expect interest to play a huge role here. And we can see it doesn't, because you would literally have to put away like $2 extra per month in order to account for the interest that this account gives you. So now let's run example 6, which is very similar to example 1 in that you are trying to save for a college fund. But this time, instead of just having a lump sum of money and plopping it into an account to leave it to bear interest for 18 years, let's see instead, so like let's say you do that calculation and you see you need $73,000 or whatever it was, some crazy amount, you're like, there's no way. Let's see if I use an annuity savings plan, what is the monthly payment needed in order to reach that $150,000. So I'm going to say similar to example 1, but this time with an annuity savings plan. Okay. Let's calculate the payment you would need to make. So the goal, let's say just to remind you about example 1, the goal was $150,000. The payment is going to be monthly, so we'll say monthly payments. Monthly payment, and that's what we're going to be asking for, monthly payment, right? Time is 18 years, right? 18 years. And what was the APR? Let's say APR was 4%. Okay, so the formula says PMT payment is equal to future value, so that goal, 150,000, times my rate, 0.04, divided by n, which is monthly, so 12. It's almost always 12, it seems like. That's a 12. Just my new marker bled a little bit there. All right. And down here, I'm going to have 1 plus 0.04 over 12 raised to the 12 times t, which is 18, and then don't forget the minus 1. Okay, this is going to tell me my monthly payment I need in order to save this much over 18 years with an APR of 4%. Approximately, and let's go ahead and calculate this. How did we do it before? Find this first and then invert it. So 1 plus 0.04 divided by 12 raised to the 12 times 18. Don't forget minus 1. And now invert it. Okay. Now times 150,000, and then times this last little fraction part, 0.04 divided by 12. Okay, so I'm getting $475.30. That would be the monthly payment needed in order to have this much money, $150,000 after 18 years. That's a lot. $475, nearly $500 a month. I mean, that's a lot, you know. So, okay. Let me ask another question. How much is she putting into this account, and versus how much is actually going to be interest earned? Well, if she's making this payment every month, so times 12, that's how much she's making per year for 18 years. So I'll multiply by 18. then, well, I'm saying she because that's what the example in the text it says, but if you are making this payment, how much are you actually putting in after 18 years? You contribute $102,664.05. So that means how much is coming from interest? Well, the end amount is $150,000, so I could subtract that, and my sign is going to be the wrong way around, but that's okay. So interest gives that difference, 150,000, which would be the amount in the account after 18 years, minus the amount you put in, which is most of it, right? But still, you get a fair bit of interest, which is 47,000, I mean, that's a lot, right? $335.95 in interest. So, okay. All right, this last example is very interesting, I think. Last example here. All right, example 7. All right. It says, assume you have just graduated from college and have obtained your first job making $44,250 per year. Currently, the national average retirement income for people with a bachelor's degree is $60,000 per year. Assuming you are 22 years of age at graduation and you will retire at age 67, then you will be working and investing for 45 years. At current rates, a mutual fund has an APR of 8%. How much do you need to invest each month in order to live off of $60,000 per year when you retire? In other words, they're asking how much do you need to have saved up so that you can live off of interest? $60,000 earned in interest per year. All right. So let me write down the question. You should read this example in the text. It's page 493. How much do you need to invest each month Now, assume the APR is 8% and you're making monthly payments. Did I say that? Yep, each month. And time is 45 years, which is, I said that in the setup for this problem. Okay. So I'm asking how much money do you need to have saved up so that just the interest is earning $60,000 per year? So first, let me start with that question. Like, what's that lump sum need? What does that lump sum need to be so that 8% of it is $60,000? So I'm asking this question. I'm saying, well, let me get my red marker. I'm asking this, 8%, which is the annual percentage rate, of what number is 60,000? So this means that whatever the number is here is how much you need in your account so that you can pull $60,000 out per year and never lose money because you're just living off of the interest. So the lump sum would stay in there. It would gain $60,000 for the year. You spend that just to, live, and then, so you're taking that $60,000 out throughout the course of the year, but it doesn't matter because it has so much money in there that the interest keeps replacing what you take out. So what 8% of what number is 60,000? How do we set this up? Remember, this is 0.08 times some number x is 60,000. It's like a percent problem, right? So we're going to solve this by dividing by 0.08 on both sides. This is from chapter 4, right? Chapter 4 is where we talked about percents, wasn't it? Or was it chapter 5? Yeah, I think it was chapter 4. 0.08. So I'll just pop that into the calculator. Aha. That seems about right. That's a lot, right? $750,000 is what you would need as the amount in the account to be able to live off of $60,000 worth of interest per year. Okay, so this is going to be our goal then. At the end of 45 years, so the goal is going to be to have $750,000 at the end of 45 years, because that's when you want to retire. So now we can ask the question, how much will that monthly payment need to be? So now we go back to the payment formula with this goal in mind. So that's my goal. My monthly payment is unknown. My APR is 8%, and my time is 45 years, and N is 12 because I'm asked about monthly payments, right? So N is 12. So here we go. PMT is equal to that goal, 750,000, that future value, times 0.08, that's R over 12, that's N there, R over 12, and then 1 plus R over 12 raised to the NT, so 12 times 45, there's that time coming into play, then minus 1. Okay. One plus 0.08 divided by 12 raised to the 12 times 45, then minus 1. Now I invert this whole thing, right? Invert. Okay. Now I'm going to multiply by 750,000 and then finally multiply by this fraction. Oh crap, hang on, I messed it up. 0.08 times. Ugh, going too fast. There we go. Okay, and there it is. So it's pretty low, $142.19 per month. This is per month. To be able to live off of $60,000 per year just in interest when you retire. So after 45 years of working. So, you know, and also more than that, you would have $750,000 in the bank, right? So you could buy a house or something, a really nice house. So that's a pretty interesting problem, you know, looking at how much do you need to have in the bank to be able to live off of some amount of interest. All right. Okay, so let's see. I'm going to come up with some extra exercise problems for this section. And then we've got the last section is 9.4, which is called borrowing money. So now we're going to look at credit card debt and all that not fun stuff, but it's, yeah, we're going to have some complicated formulas involving logarithms actually. So we do get into logarithms a little bit, but all the formulas are built for us. So. And we are ahead of schedule, so we can take a lot of time on 9.4. Okay, this is it for 9.3.